Let's take a look at the number e. When I say that, I always feel like I'm in an episode of Sesame Street where today the letter of the day is e. But wait, it's not the letter, it's the number e. I know that seems strange, but the number e is an irrational number. It shows up in a lot of mathematical places. So remember, irrational means that decimal goes on forever and ever and ever with no repeating pattern, similar to pi. Okay, let's look at a couple of examples of how this shows up. We have growth of a bacteria given by n of t equals 200 e to the t, where t represents the number of hours after the start of the experiment. How many bacteria are present at the beginning of the experiment? Well, the beginning would correspond to t equals 0. So n of 0, 200 e to the 0, that would be 200, because e to the 0 would be 1. So 200 bacteria. The reason we're talking about this here is because this is an exponential function. It's an exponential function with base e, which is that situation of bigger than 1, since e is approximately 2.7182. And then the 200 would be a stretch factor of that. How many bacteria will be present after 30 minutes? 30 minutes is going to correspond to t equals 1/2. So n of 1/2 would be 200 e to the 1/2. I'm gonna have to throw that in my calculator and approximate it, because the square root of e, which is that e to the 1/2, is irrational, right? So what I get out of my calculator is 329.7. So we're going to say 330 bacteria after 30 minutes. Because you have to have a whole number there, right? And then let's do the same. I'm going to try and squeeze it in here. N of 4, 200 e to the 4th. E to the 4th times 200. Wowza. Approximately 10,920, if we round that to a whole number, bacteria after 4 hours. That gives you an idea of the power of exponential growth. We had 200 bacteria to start with. I'm picturing like a petri dish, right? Where we spread some bacteria in there. We start with 200 bacteria. After half an hour, 330 bacteria. So not quite double after half an hour. 4 hours, we're at almost 11,000 bacteria. That is the power of exponential growth. It grows so quickly. And that's what we saw sort of in that coronavirus graph, right? And that was the concern, is how quickly it spreads. The next question, part C here, says, when will 2,000 bacteria be present? The when is find t when n is 2,000, right? So that would be 2,000 equals 200 e to the t. I can divide both sides by 200 to give me e to the t equals 10, but I don't really know how to solve that, right? I don't know how to deal with that t. I can't divide by e because it's not e times t. That doesn't make sense. It's e to the t power. So I'm struggling to deal with that t in the exponent. And that's something new with these exponential functions, right? So let's try some guess and check. One thing that we do know is that it's somewhere between half an hour and 4 hours, right? Because half an hour there were 330, 4 hours there's almost 11,000. So 2,000 is going to be somewhere in there. So let's just try. What if we do t equals 2? And I'm just going to plug that in. I get e to the second is 7.389. So that's not quite big enough. E to the 2 is approximately 7.3. Let's go 39. That's not 10. I need to go bigger, right? What if I go e to the third? That is going to be approximately 20. Okay, well that's too big, so I want to go somewhere in between. T is 2.5. I'm just throwing these in my calculator, trying to guess and check here. You could do this nicely in the table feature of your graphing calculator that we talked about before. E to the 2.5 is approximately 12. So you could see that we could keep going here, but this is not super sophisticated, right? 2.3. Try that. E to the 2.3. Oh, that's better. 9.97. So if we rounded that, that's pretty close. So approximately 2.3 hours. After approximately 2.3 hours, we'd have 2,000. But guess and check is kind of not the most sophisticated way to deal with this. So I think we'd like to see a different method for solving that. And we are going to see that in the upcoming sections, the upcoming topics. Compound interest. Compound interest is very, very powerful technique, or very, very powerful way to earn interest. What happens with compound interest is that you earn interest on your interest. For example, let's suppose you start with $100. And then you don't touch it, you just leave it there, and suppose it grows to $102 over 1 year. Let's say you have 2% per year. Okay? That's what you're earning. 2% of $100 is $2. So you add the $2. Now, if you do 2% of the 102 instead of just the $100 that you started with, so you earn interest on your interest, you get 102 with that 2% is $104.04. So instead of just earning $2 like you did in the first year, the second year you earn $2.04. Well, in a small interest rate and a small dollar amount, that doesn't seem like a huge difference, right? But if we keep doing that, instead of on the $100, it really starts to grow really quickly. Let me show you an example of how powerful compound interest can be. Occasionally I listen to a financial guy named Dave Ramsey, and this is an illustration that he has created to help you understand the power of compound interest. This he calls the story of Ben and Arthur. What you see here is Ben investing, and he starts at age 19, and he invests $2,000 per year every year until he's 26 years old. Arthur, alternatively, waits until he's 27 years old and he starts investing $2,000 every year until he is 65 years old. Okay? So the question seems like, okay, Arthur invests a whole lot more total money, right? From age 27 all the way to age 65. But, and then Ben invested nothing else except for this, what, 2, 4, 6, 8, 10, 12, 14, $16,000 when he was 19 to 26. Arthur investing a whole lot more. If you look at the bottom line, at the end of this, and this is assuming some pretty aggressive interest rates, so don't get too wrapped up in the numbers, because this is probably not very realistic numbers, but the growth is the important part. The Ben has almost $2.3 million. Arthur has $1.5 million. I'm not going to cry about having $1.5 million, but obviously starting earlier and seeing how that interest, see, it just grows. And like by the time Ben gets to, age 45 or say 50 here, in 1 year he's earning, $50,000 in interest, and then it just starts to get really, really a lot of growth. Here he's earning over $100,000 in interest in 1 year, whereas in the first year he earned, after he stopped investing, he only earned $3,000 in interest, going from $27,000 to $30,000. Down here he's earning, $100,000. That's the power of compound interest. You continue to build and build and build and build, and the earlier you start, the better off you're going to be. Don't worry, you're not doomed if you haven't started investing yet. You will still have an opportunity. Don't worry. That's the exponential growth, though, that we see. And that is what you see with compound interest. The formula that is used for investing P dollars at interest rate R, compounded N times per year. After T years, the account will have P times 1 plus R over N to the NT power. If the interest is compounded continuously, a part of this goes to the real number E, that irrational number E. Let me write this here. PE to the RT. So you use the E there. And that comes from something that we study in calculus, how you get from here to here. But this is if it's compounded, if interest is compounded continuously. Up here, when we talk about compounding N times per year, maybe your checking account gets interest added into it 1 time per month. In that case, the N would be 12. Compounded continuously would be just if it's added always, continuing to add and add and add, which doesn't happen in a practical situation. Okay, determine how much money you will have in your savings account. Oopsie. I think that's supposed to say in 20 years, if the account currently has $5,000 earning 8% interest compounded monthly. Up here, we need to know P, R, N, and T, and that'll tell us A, how much it'll grow to. So P, R, N, and T are the things we need to know. P stands for principal. It's how much you start with. It's $5,000. The rate, an important idea here is that this has to be the rate in decimal form. 8% is 0.08. N is the number of compounding periods per year. In this case, that is 12 because it's compounded monthly. And T is the number of years, 20 years. So A will be 5,000 times 1 plus 0.08 over 12. That actually tells you, the rate is an annual rate. That when you divide it by 12, that tells you how much of that you earn per year. And then to the 12 times 20 power. So notice this is exponential because we've got that the variables in the exponent there. 5,000 times, this is actually going to give me a decimal, so I am going to, I don't like to round until the very end, so I'm going to follow order of operations when I put this in my calculator. 0.08 divided by 12, I hit enter, plus 1. Then I'm going to raise that to the, and you might want to write this down. I don't want to divide, like actually divide that because I would have to round. I'm going to raise what I just found to the 240th power, then multiply by 5,000. And it gives me $24,634.01 is how we use that formula. Compounded quarterly, the only difference is now the n changes to 4. Quarterly would be 4 times per year. So 5,000 times 1 plus 0.08 over 4 to the 4 times 20 power. This one I could actually do the calculation because 0.08 divided by 4 is 0.02 exactly. But this one up here is going to give me a decimal that goes on forever and ever, so I don't like to do that. So that's 1.02 to the 80th power times 5,000. 24,377.20 is what it would round to. 2 decimal places for money. I have a question for you to think about. Does it make sense that we got a smaller number from quarterly compounding versus monthly compounding? I want you to think about that for a second. Remember, compound interest is earning interest on your interest, right? When your interest is compounded quarterly, which would be common for like maybe a savings account, like a kid's savings account, those often you get interest added every 3 months. When it's compounded quarterly, you have less opportunities to earn interest on your interest than when it's compounded monthly. So we do have a little bit extra money here when it's compounded monthly because it's added, interest is added in more often. It'll be less interest added each month, less, the monthly interest is going to be less than what you would get over a quarter, right? If you earn $4 in a month, 3 different months, $12 total over those 3 months, that quarterly amount might have been, $11.50 or whatever, if it's only added in one time. So that's the idea, is that hopefully you can see that it makes more sense. You're going to earn more, you're going to have more total money if it's compounded more often. Compounded continuously, we are just using that formula, PE to the RT. P is 5,000. E to the R is 0.08 and T is 20. The rest of it, the compounding periods, are kind of worked into that E. So 5,000 E to the, what is that, 0.16? Or 1.6. Yeah, 1.6. So let's do E to the 1.6 power. And then multiply by 5,000. And that gives us a number. Would you expect it to be bigger or smaller than the monthly compounding? It's added more often, so it should be bigger than the monthly compounding. $24,765.16. That's compound interest. It's just a cool application of exponential functions, so I wanted to show it to you here.